Welcome to the deep dive. Today we're jumping into something pretty fundamental for large language models, positional encodings.
Uh-huh.
And we're focusing specifically on rotary positional encodings, rope.
Yeah, rope, it's everywhere now, isn't it? LLM3, Gemma.
Exactly. So understanding it feels, well, crucial, but we've been digging into this recent paper and it really challenges some common ideas about how it actually works inside these models.
Right. And if you're listening games you like getting to the heart of complex stuff without wasting time, hopefully getting those aha moments, this is for you. We're using our note and it's a really great paper, Unpacking Positional Encodings in LLMs, Rope and Beyond, to get past the basics.
Yeah, our mission here isn't just the textbook what is rope explanation. We really want to explore the, let's say, more academic side, the innovative bits. How are these models really using ropes? What are the sort of unexpected tricks they've learned?
Okay, let's get into it.
All right, so the standard story, maybe even from the original rope paper, is that it helps the model pay less attention to words that are further away, right?
Yeah, that's the common intuition. Closer words, stronger connection, makes sense.
But this paper we looked at, it says, hang on, it's maybe not quite so simple.
Exactly. It argued that this neat decay often relies on um, a big assumption that the query and key vectors, how the model asks and finds info, stay constant.
Which they definitely don't in a real LLM, right? It's messy in there.
Far from it. And what's really cool is Proposition 3.1 in the paper. It shows that if you set up those queries and keys just right, a transformer using rope can actually pay maximum attention to any relative distance it wants.
Any distance. Wow. So much for simple decay. That shows a lot of flexibility.
Incredible flexibility. But then Proposition 3.2 takes it even further. It asks, okay, what happens with more typical queries and keys, the kind you might actually find, like sampled from a standard Gaussian distribution, mathematically speaking?
And the result?
The expected attention, 0. Doesn't matter how far apart the words are.
0. Okay. That definitely throws cold water on the simple distance decay idea. They showed that experimentally too. I remember seeing that in figure 2.
They did. So the big takeaway here is rope's advantage isn't solely about making attention fade with distance. There's something else, something more subtle going on.
Which leads us to how models like Gemma 7b, and they found similar stuff in Llama 3.18b, apparently actually use the different frequencies inside rope.
Right. So rope works by sort of splitting the query and key vectors into these little 2D pairs.
Like little dials.
Kind of, yeah. And each pair gets rotated, but at a different speed, a different frequency.
Okay. And when the researchers looked inside Gemma 7b, what did they find? What stood out?
Well, figure 3 really lays it out. Across basically all the layers, they found much higher norms. Think of it as more influence or importance assigned to the slowest rotated frequencies for both queries and keys.
The slowest ones. So Gemma actively learns to prioritize the slow, gradual rotations over the fast ones.
Seems like it. That's a key aha moment, isn't it? You might think the fast changes are important, but overall, it's the slower shifts that get amplified.
Feels a bit counterintuitive, yeah.
It does. Although the paper is careful to point out exceptions, there's some higher frequency use, especially in the very first and last layers,
Uh-huh.
and also in very specific attention heads. Figure 4 highlighted a couple, heads 5 and 8 in the first layer, I think.
Right. And these high norm bands, this concentration of influence on the lower frequencies, the paper floated an idea connecting this to sparse semantic matching, something about feed forward layers acting like dictionaries. Can you break that down a bit?
Sure. The idea is like these strong signals at specific low frequencies might let the model tune into and match specific kinds of meaning or semantic content, almost like dedicated channels.
Okay.
And these slow rotations could provide a kind of stable background for those channels to work reliably, picking out specific semantic patterns.
Okay, so low frequencies seem linked to meaning, to semantics. But what about the high frequencies, the ones Gemma mostly tunes down? The paper argues they have a very different, very specific role, positional attention.
Exactly that. The heads that do use the highest frequencies, they tend to show these purely positional patterns. Figure 5 had those great examples, right? Like a diagonal line where a word attends to itself.
Yeah, or just looking at the token right before it.
Precisely. These heads seem to care only about where the words are relative to each other, not what they mean.
And this isn't just an observation, is it? The paper actually shows why rope can do this, theoretically.
It does. Theorem 5.3 mathematically proves rope can learn these diagonal or off-diagonal patterns, which is interesting because Proposition 5.2 shows that models without positional encoding, nope, can't reliably do this. They get confused if you repeat words.
Oh, okay. And how does rope manage it?
Well, the proof involves a clever construction. For diagonal attention, you basically set the query and key vectors to be the same. For off-diagonal, like attending to the previous token, you kind of reverse the rotation for the key.
And the amazing thing is, they found evidence that Gemma 7b is actually doing something very similar. It's not just theory.
Exactly. Section E.1 in the appendix suggests Gemma learns a construction strikingly like the one in the theorem.
Wow.
And those high frequencies are crucial because they rotate so fast. Even a tiny shift in position causes a big change in the dot product, the similarity score.
Which allows for that super precise positional focus, like in Figure 6, for that diagonal head in the last layer.
Yep. High frequencies give you that sharp positional knife edge.
Okay, so summarizing, high frequencies give precise position awareness. Low frequencies seem to be used for semantic channels. But didn't the paper also raise a concern about those low-frequency semantic channels, especially over longer distances?
Ah, yes. Theorem 6.1. It argues that rope fundamentally struggles to create truly robust semantic channels over very long contexts.
Why is that?
It's down to the math of the rotations. They use irrational numbers, and these rotations become dense over long stretches. Think of it like the patterns get messy and unpredictable the further out you go.
So it's hard to maintain a consistent semantic signal based on a specific low-frequency alignment if the text gets really long, like interference patterns.
That's a good way to think about it. Small variations accumulate and disrupt the signal, which kind of brings us back to Gemma boosting those low frequencies. It seems like it's trying to build these semantic channels, even with this limitation.
And maybe that explains why things like increasing the base wavelength in rope, like Llama 3 does, helps with long contexts.
Precisely. Slower rotations mean the patterns change less drastically over distance, so maybe the semantic information can persist longer.
Right. Okay, building on that problem, the paper introduces a really interesting modification, p-rope, partial rope.
Well, p-rope, yeah, the p isn't explicitly defined as partial, but the idea is to modify rope. The motivation is exactly that problem of unstable low-frequency semantic channels.
So what does p-rope do?
It does something quite radical, actually. It just removes the very lowest frequency components from rope entirely.
Removes them, you mean it just zeroes them out?
Effectively, yes. The idea is that by cutting out these potentially unstable low frequencies, you might actually create more robust, distance-agnostic semantic channels with what's left.
Huh. Removing information to improve performance. That's bold. Did it work?
Well, look at Table 2. They tested it on Gemma 2B. And p-rope, the version that truncated the lowest frequencies, either maintained or sometimes even improved performance compared to standard rope.
Better than standard rope, and also better than just removing positional info altogether, the no P baseline.
Yeah. And significantly, it also did better than alternatives like only increasing the wavelength or only removing the high frequencies.
Okay, that really points the finger at those very lowest frequencies being the source of that non-rebuffness, doesn't it?
It strongly suggests it. It implies that both p-rope and just making the rotations slower, increasing wavelength, are getting at the same problem, trying to stabilize those low-frequency channels for longer ranges.
And the paper mentioned this relates to some other ideas too, like rope partial.
Yeah, they drew parallels. Rope partial rotates only some dimensions. P-rope is similar in spirit, but provides this specific mechanistic reason. Get rid of the problematic low-frequency rotations.
Okay, let's try and wrap this up then. Key takeaways from this deep dive. Rope is definitely more complex than just making attention decay with distance.
Absolutely. High frequency seems crucial for very precise positional attention, knowing exactly where words are relative to each other.
While the low frequencies are what the models seem to want to use for semantic meaning, but they run into robustness issues over long texts.
And the really innovative part of this research, I think, is how it digs into the mechanics, showing how LLMs learn to manipulate these frequencies for different jobs. It's not just using rope, it's skillfully exploiting its properties.
Definitely. And P-rope stands out as a genuinely novel technique born from that understanding. It suggests a concrete way to potentially improve long context performance.
Yeah, it feels like a really promising avenue for more work.
Which leaves us and you listening with a final thought to chew on.
Right. If LLMs are learning these sophisticated tricks, manipulating fundamental things like positional frequencies in ways we're only just uncovering, what other deep mechanisms are hiding in plain sight within these models? And, what happens when we finally understand them? Could that unlock even more capable, more efficient AI down the line?
Something to think about. Thanks for joining us for this deep dive.